Hello and welcome back to Physics for the 21st Century. Again, my name is Greg Perugini and I'll be guiding you through this topic, kinematics. So let's move on. Kinematics is describing motion. We're describing motion. In this point, we're talking about motion in one direction. And that direction could be from side to side, from one point to another, either horizontally or vertically. Now, these equations that are developed as part of kinematics came from Sir Isaac Newton. And with those equations, we have to assume constant acceleration. We're not working with any external agents that might have caused or modified the motion yet. We're not talking about force. We'll get to that later. So motion is a continual change in position. We have several types of motion. Now, we already talked about motion in terms of a velocity, which is simply a change in distance, or I should say displacement, for a period of time. This motion being, as I said, either vertically or horizontally, we're talking about calling that either linear or translational motion. The other two, rotational in a circle or vibrational back and forth, if we're talking about a pendulum or simple harmonic motion, we'll get to later. We're going to be using a particle model. Mass having an infinitesimal size, but still being mass. We'll take mass into consideration when we talk about force later. So these are the kinematic equations, these four equations that we'll be dealing with. And those four equations we're going to use, and as you can see here, we have several variables that we're talking about. Right? If we look at these, for instance, that first one up here, obviously you don't see position in this one. You see position in this one, but you don't see acceleration. So depending on what variables you have and what variables you're missing depends upon which kinematic equation you'll use. Let's look at an example here. Let's say we have a car. Okay, and forgive my drawing, I'm not very good at drawing, but that's a car. And this car is going from rest to 60 miles per hour in 4.9 seconds. Very fast car. So we can look at this car and figure out, or the question could ask us several things, and one of the things it could ask us is, what is the acceleration? Or it could ask us, how far did it go? Well, I'm going to put up here now the kinematic equations. I have them written so we can refer to them on a regular basis. So let's put that right here. Okay, so there we have them so we can refer to them. So what do we know here? For this problem, we're racing down the highway here. We know that t equals 4.9 seconds. In these equations, that's what I know. Our velocity initial, well, we're starting from rest, 0. So we're doing this in this time frame, and we're going at a velocity final of 60 miles per hour. Well, the first problem we have is that is not standard. We can't use that. we have to translate that. So let's look at what we have to do here. We have to do our dimension analysis to solve that, right? So 60 miles per hour, right? Or 60, let me write it a little clearer here, miles per hour. And there are, in 1 hour, 3,600 seconds. And there are 1,609 meters in 1 mile. You see what happens here is that, just like we did with dimension analysis, miles are going to cancel, hours are going to cancel. All I'm left with is meters per second, which is the standard SI unit. If we do this math, we will get 26.8 meters per second. And you can verify that on your, let's put that right here in one of those things that we know. 26.8 meters per second. So given those variables, the first question is, what is acceleration? We don't know what acceleration is. But I could certainly solve for that, right? Given the kinematic equations. Which one would I use? Look at them carefully. It looks like I can use velocity final equal velocity initial plus AT. Looking at that equation, velocity final 26.8 is equal to velocity initial 0 plus acceleration, that's our variable that we're looking for, in 4.9 seconds. Well, our math is pretty easy on this. I could solve for acceleration, and I'll give you a second. You can pause it here. What would acceleration be? If you solve that, you should get 5.46 meters per second squared. So now we know that. It's no longer an unknown here. 5.46 meters per second squared. Now the second question asks, how far did it go? Given these variables here that we have defined in our problem, as well as calculated in terms of acceleration, we need to find change in x, change in displacement. Well, looking at these equations, I could use the second equation, or I could use the third, or the fourth. I could also use the third too. Any one of them I would use to solve for that change of x. Right? I could put this over here, x final minus x initial, and that is a change of x, as well as over here. I'm going to use the fourth one here. Velocity final 26.8 squared is equal to velocity initial 0 squared plus 2 times 5.46 times change in x. Again, very simple algebra. We should be getting here change of x equals about 65.8 meters. So that's the second part of this equation. What is the acceleration? 5.46 meters per second. What is the distance it went? 65.8 meters. It's a fairly simple example. Let's turn it up a bit and go to a little bit more complex problem. Okay, I'll put that up here like that. Let's say we have a rocket sled. And at rest, it begins the race, gets to a speed of 250 meters per second. That's pretty fast. It's really moving. Then it deploys a chute. Which slows it to, or I should say at a rate, let's do it that way, at a rate of 3 meters per second squared. Total distance. What is the total distance from the start of the race till when it stops? That's what we have to solve for. So, I should also say that it does this acceleration in 5 seconds, let's say. So what do we know? T equal 5 seconds, and I encourage you to write out what you know, just so you are fully up to speed with it and get clear in your mind what's being asked for and what you already know. So velocity final, 250 meters per second. Velocity initial, well, we're starting from rest. So this is the first part of that problem. We're going to call that the first part. We've defined the problem. Now we're going to say, okay, that's the first part. We're looking for that distance in that first part. And in the second part of it slowing down. So how do we get that first part? So part 1, looking for a change in distance. How do we get that? Well, given these equations, what's the first thing that we can solve for? Well, here I'm looking for the change of distance, but I don't know the acceleration. I don't know the acceleration. I could use that second equation. X final minus x initial is the change in distance, is equal to 1/2 velocity final, 250, plus 0 times time. By the way, I could have also used this first equation to get acceleration, and then use that in this equation to get the change in displacement. Either way, all these 4 equations, all 4 of these equations are self-consistent. You better get the same answer for all 4, or it isn't constant acceleration. So, looking at this equation, we do know the time at 5 seconds. So given that time at 5 seconds, what is the change in distance? do the calculation yourself, and you should get 625 meters. So for part 1, change of x of part 1 is equal to 625 meters. Well, part 2. Our velocity initial for that second part is the velocity final of the first part, 250. We don't know the time it takes, and maybe that's a question that we can answer later. But we do know that the velocity final is it's going to come to a rest at 0. We know our acceleration is a negative 3 meters per second squared. The chute is slowing it. So, what is the change of x for that second part? Looking at these equations, see if you could figure out what kinematic equation I should use. Because we're given acceleration and we have the two velocities, it seems like this fourth equation is going to fit nicely. Velocity final squared, so let me just write that down. 0 squared is equal to velocity initial, 250 squared, plus 2 times acceleration is negative 3 times change in distance. Change in distance is equal to, if you do this calculation, you should get 10,417 meters. The chute sort of slows it down, as it should, slowly. So there's our two parts. This being 625, this being 10,417. So the total distance, the answer is, the addition of both of those together, about 1,042 meters. So, when you're solving these type of problems, think about and try to understand the situation. Sketching it out would help. Gathering the data, writing down what you know, and looking for the algebraic meaning of the phrases. I deploy a chute and it slows it down. So that's a deceleration. I'm starting at rest. Velocity is initial is equal to 0. I am coming to a stop. Velocity final is equal to 0. And make sure your answers are reasonable. If I come up with an answer here of 15 miles or 15,000 miles, obviously I've probably done something wrong with my equations. So keep that in mind. Try to look for reasonableness. Also understand what a vector is, because these kinematic equations work with the vectors of velocity and acceleration. And we could do this in many dimensions, or in any dimension. We'll be talking about in the y direction using these equations for free fall. Using in both directions, we'll be using it for projectile motion. Again, make sure your answers are reasonable. You may need dimension analysis like we did in the first problem to convert miles per hour to meters per second. And of course, practice is important. You want to know these equations pretty well so you can go back and forth using each individual equation and doing your calculations on your calculator without thinking too much about it, understanding the concepts and the root of these kinematic equations. Remember, we have to be talking about constant acceleration to use the kinematic equations. So that should be all you need to know for this fifth topic, kinematics. Good luck.